The second part of the chemical senses is to talk about olfaction. So we'll start with that. So I'm going to say this another way, and we're going to start here of saying most of what I just said. I usually do this first. I like talking from pictures and then going back and making sure I use my words, I use the language. But so if we're looking at what's happening here, and this is going to introduce some things as well. So if we're looking at what's happening here, we have those colored things, the orange, green, and purple, are olfactory receptor neurons. Okay, and that they are in the olfactory epithelium where we have more support cells. And then if we look at the cilia, those little what look like little hairs coming out, that the olfactory mucosa down there is also it's moist, and so driving those odorants to those cilia to affect those olfactory receptor neurons. They're going to communicate up through the olfactory nerve through the cribriform plate and to the olfactory bulb, which is lying there on top. And the other thing they show with this picture is that if we look at that green kind of diamond thing, that it's receiving information from those green olfactory receptor neurons. So that would be a particular olfactory receptor neuron type. And so a particular type of olfactory receptor neuron is going to go to what's called a glomerulus on the olfactory bulb. They actually go to a pair of glomeruli, usually, is my understanding. That there's usually two of these, and then we're sending that particular type of olfactory receptor neuron they're all sending to that particular glomerulus, or that pair of glomeruli. And again, this is the olfactory receptor neurons. They are doing the transduction. And if we look at what's happening at those olfactory receptor neurons, in this study by Malnick et al., what they did was, so they presented things like octanoic acid and octanol. Let's choose those two because they're nicely similar in molecular structure. And then they went and saw, so which of these particular, so they looked at a number of olfactory receptors. Are they firing, right? And what's their firing pattern? If we're looking at a firing pattern. And so octanoic acid, it has 1, 18, 19, 41, 46, 51, and 83 all fire strongly, and 79 fires a little bit. Octanol, which is very similar, we're just missing a couple carbons and an oxygen, I think. So it is firing, it is causing a different, what's called recognition profile. 18, 19, 41, and 51 are all firing strongly to the octanol. And so while they have similar molecular structures, these two odorants are going to smell different from each other. And because I never remember which one smells like what, I'll go on to my wordy words and say, so octanoic acid smells rancid, sour, and repulsive in comparison to octanol, which people describe as rose, sweet and fresh. So really quite different from each other. And we can see that they're going to smell different from each other because they have these different recognition profiles. They have a different pattern of firing across those neurons that the researchers examined. A couple of additional just things that I have said, but here we go. The axons of the olfactory receptor neurons pass through the cribriform plate, this kind of bony structure. They bundle to form the olfactory nerve, and that goes to the olfactory bulb. And we synapse on the olfactory bulb with a pair of glomeruli receiving information from a particular type of olfactory receptor neuron. We can do this comparative from bloodhounds to humans, and you might notice that these estimates are just slightly different from what we saw before. But bloodhounds, they have estimated have 220 million olfactory receptor neurons compared to our about 10 to 20 million. And the other piece here, so we've talked about this a few times, that if I have more neurons communicating to a part of the brain, directly, then they get representation and they get more cortical space. And so when we look at the cortical space, 5% of a bloodhound's cortex is devoted to olfaction. So they're going to be more consciously aware of it, they're going to pay more attention to it, and they're going to be having a stronger experience than we do. Our cortex, about 0.1% of our cortex is responding to smell. And then I have a picture of my puppy when he was a puppy, because the first time I ever made videos was during the pandemic, and I got this puppy, and now he's a grown dog, and I can share pictures if anybody asks me, because he's adorable and he's sweet and he's so well behaved. And yeah. Okay, and there's a nice picture comparison too. If we look at the olfactory bulb in humans, you can see it's narrowed out quite a bit in comparison to, I actually think that might be a rat brain. So we have this convergence, really like we saw with the rods, right? And in the peripheral retina, we have this convergence where we have about 20 million olfactory receptor neurons communicating to about 6,000 glomeruli. And this is where I say on the slide with the language, what I've said twice now, that all of the olfactory receptor neurons expressing a particular type of olfactory receptor neuron, they converge onto one glomerulus pair. So, for example, all of the olfactory receptor neurons that are responding to methyl salicylate send axons to a single glomerulus pair. And that's what they're showing with the red. They did that with the green, orange, and purple before. Here we're doing with red and blue. What this means when we get to the olfactory bulb. So remember, we had this olfactory receptor like recognition profile for certain smells, and the more similar those recognition profiles, the more similar the smells. So it has less to do with so much the molecular structure, but the recognition profile. But on the olfactory bulb, those molecular structures that are similar to each other, they are close to each other on the olfactory bulb. And and I don't know, this is a bizarro factoid, but the longer the chain, as we get to a longer length, the farther forward it goes. Your authors, and this says the farther to the left, but from what I can see of how the olfactory bulb is positioned and shaped, it looks like it's moving forward. So the shorter the molecular structure, they're farther back. And then the other ones with similar molecular structures are going to be close by, but moving forward. And so this is the activation that they measuring oxygen consumption. But we're going to see another measure of what's going on at the olfactory bulb with this one, where the olfactory bulb, because of this, is often talked about as having an ototopic map. I'm pretty sure I stick to ototopic map, but I might accidentally say chemotopic map sometimes. I think I've changed over the years that I went more to ototopic map. But it's a little bit both, right? Because it's the chemical, it's the structure, but it's also the odor. Both of those things are being coded on the olfactory bulb on this odor map. So if we look at this one on the left, where we have plus carvone and minus carvone, but otherwise they are a very similar molecular structure, you can see that they are activated in similar places in similar amounts, with the red being high activation, red and yellow, green and blue being low activation. But notice where the white arrows are pointing, they smell different, and there are these differences where the plus carvone has up at the top and kind of over to the right, they have a little bit more activation. And the minus carvone doesn't have so much activation there, but if we go kind of a little bit to the lower right, there's a lot of activation. We look at the ones that have similar molecular structures and similar smell, so they smell the same, the plus limonene and minus limonene, they look really, really similar. So it's really coding for both. The different chemicals, well, the different chemicals in the chain length, it's coding for all three, and and our different perceptions. Now, so one of the eReserve journal articles that I've included in here since I started teaching this, and not since I started teaching this, but close to when I started teaching this in 2012, and I started having eReserve soon after, maybe 2015, 2016. And I included a 2012 article, which I will never get rid of because I've never seen anything like it. It's amazing research. It's a beautiful design. It's difficult to understand the methodology and kind of difficult to understand what they're saying. But if we look at this picture and what they're showing us in the textbook, and this is why it's so good to read in the field, because what the textbook is doing is it's really taking lots and lots and lots of research and simplifying it for you into a story of here's kind of the perceptual system. But if you look at the specific research, it's so much more complicated. But so once we get to what we do is we send information from the olfactory mucosa and from those olfactory receptor neurons to the olfactory bulb, and then it sends its information to the piriform cortex and to the amygdala. And the piriform cortex is what I'm used to calling the primary olfactory cortex, but you could include the amygdala in there as well, but we all know, right, that the amygdala does a lot of processing and a lot of emotional processing. And I say we all know this, right, because oftentimes people have been if they know anything about the brain, they're like, yes, I know about the amygdala, it tells us about fear. Well, I'm going to say it's a little more complicated than that. It's more about emotional processing, especially when something's ambiguous, tying those things together. It's about associative learning and conditioning. It's about all of those things. It's doing all of those things. And so the fact that smell goes right in here suggests that there's something very strong about smell and our memory. And then piriform cortex, they have piriform cortex communicating to the amygdala and also up to the orbitofrontal cortex. But you can see where I've added in here in parentheses, because it's very important, it also travels to these other limbic structures. So the limbic system, our emotional, motivation, memory system, has a lot of these regions that are basically coding emotionally associated memories. And so giving us these really complex experiences that when I start talking about smelling sticky buns and being transported back and having these vivid memories, those sticky buns, that smell is going into the piriform cortex, into the amygdala, but also then immediately to the rest of the limbic system. The hippocampus, the entorhinal cortex, the parirhinal cortex, all of these areas that feed into the hippocampus, so all of these areas related to emotion and memory, and also to the prefrontal cortex. So that orbitofrontal cortex, it is the part of the frontal lobes that is above the orbits of the eyes. So it's medial, it's right above the eyes, it's in the middle of the brain. So piriform cortex is communicating across the cerebral hemisphere. One thing to talk about when we're talking about this higher order olfactory processing is really how do we recognize odor objects, right? This is what we've done with vision and with hearing. We got to higher order processing where we are, hey, we're not just perceiving this, we're not just consciously experiencing features anymore, we are recognizing. And so when we get to smell, we rarely smell one chemical in isolation. So coffee by itself has more than 100 different molecules. But we're often not just smelling coffee by itself, right? We smell coffee with maybe orange juice and bacon odors also present. And they show this picture in the book, and I'll just ignore orange juice because that doesn't seem like a very strong smell to me. But bacon and coffee both come wafting at you, right? With all of their various molecules. And we are smelling coffee and bacon as opposed to these things that are really mixed together in such a way that it's amazing that we separate them into these separate odor objects. So how do we do this? How is perceptual organization happening for olfaction? This is a major question. I'm leaving it up there for a second. I'm going to go ahead and remind you that for vision and hearing, we talked about things like similarity, good continuation, proximity, common fate, synchrony, and meaningfulness and familiarity. So what do you think? Are we using all of those? Are we using anything else? How are we recognizing coffee? Those hundreds of different molecules that make up coffee while they're mixing with those molecules that are making up the smell of bacon. I've gotten some really good answers for this over the years, I will say. And typically, and at first, everybody would say familiarity, and meaningfulness, all of this background knowledge. Imagine walking into Starbucks. It's easier to notice the smell of coffee than maybe other smells because you know that you're going to smell coffee. I've had other people throughout the years come up with other aspects of maybe the synchrony and the timing of those odorants hitting your nose, the proximity of themselves. Maybe they're not mixing as much as we think, and maybe some of them are closer to us, or the odorants are closer to each other. Maybe similarity probably has a big piece of it, because if we have two different maybe perfumes and we're sitting next to gardenias and these perfumes are those flowery perfumes, maybe those would be more difficult to distinguish than something like coffee versus bacon, which are more dissimilar. Yeah, it's a fun thing to think about, and I hope that you were thinking, that you were pausing and thinking and kind of thinking this is cool. But top-down processing, I would say we use a lot of top-down processing for olfaction. I'm going to bring us back to our picture because we're going to talk about higher order olfactory processing, and specifically the piriform cortex and how it is really different than the olfactory bulb, and how it is really different from other primary receiving areas. The other thing I should say here, because it's good to see it on the picture while I'm talking, notice that this information is not going through the thalamus. Our little librarian of our brain is not filtering, sorting, summarizing before getting to the piriform cortex. It's going straight there. Piriform cortex. We have the odor object, the rose, and it's giving off these molecules that we are smelling. The odorants are then causing a specific kind of ototopic or chemotopic map on the olfactory bulb, and that's going to be what happens with that particular odorant every time we smell it, because that is the influenced by the molecules themselves as well as the perception. And then, without going through the thalamus, we go to piriform cortex and we see this widespread activation, where that widespread activation is those neurons communicating across the cerebral hemisphere, and then those connections can change depending on experience. And so the more we experience this rose in the same kind of context, the stronger those connections, just like we see in regular learning, where those neurons that fire together wire together. And so that's what the last picture is really showing, is that those neurons are going to have connections with each other, but they're going to have connections with neurons across the cerebral cortex, and those connections are going to get stronger and stronger the more we experience that rose smell, especially in specific contexts. And so looking at this, this idea, Donald Wilson did a study looking at rats where he gave them isoamyl acetate, which kind of smells a little bit like banana, and then a mixture of isoamyl acetate mixed with peppermint. And he gave the rats either 10 seconds to sniff these two, either the component by itself or the mixture, and the mixture. So about 10 seconds gives them about 20 whiffs or sniffs, or he gave them another set of rats 50 seconds, or about 100 sniffs. And so they really get to know that a little bit better. And what he found was that Sniffing them for 50 seconds, they found neurons fired more rapidly to the component, and then the rat seemed to be able to pick out, or was able to pick out the component from the mixture. So influences neural firing and influences learning and remembering a particular smell, being able to differentiate it from other smells. Where olfaction gets processed is the orbitofrontal cortex, which we might think of as those higher level association areas that we typically see after the primary receiving area. And the orbitofrontal cortex is again in the frontal lobes above the orbits of the eyes. And this is an area that is assigning an affective value to stimuli and experiences. So here's a fun study, maybe not the fun study to be in, but a fun study to talk about, where they had people smell either a mixture, they did smell a mixture of isovaleric acid, which smells kind of like sweat, and cheddar cheese flavoring. And that sounds kind of gross. And if they were told this is cheddar cheese, they rated that as more pleasant than if they were told that this is body odor. They rate it as less pleasant. And what they end up seeing as far as, so here's my pleasantness ratings, my affective value, and what we can also see is that this is borne out in the activation of the orbitofrontal cortex, that for the cheddar, if they were told it was cheddar cheese, they're rating it as pleasant, and we see more activation of that orbitofrontal cortex. If they're told it's body odor, they're rating it as unpleasant, and it almost looks like to me like there's some amount of inhibition of this area, almost like this, I don't want to think about it, is my colloquial way of talking about that neural reaction in the orbitofrontal cortex.